Hi everyone and welcome to this video. So last time we introduced a few interesting concepts coming from machine learning, in particular artificial neurons, and we have seen how to connect those artificial neurons to create artificial neural networks. And in particular, we have been focusing a little bit on feed-forward artificial neural networks, and we have seen how to implement a neural network inference in the Atari BASIC. So we are going to continue with neural network in this video, but we are going to focus now on a different kind of neural networks. In particular, we are going to introduce Hopfield networks, the main concept, what they are used for, and then eventually we are going to see how to train those Hopfield networks and how to evolve them in order to make them do things that are interesting and useful. We will go through an implementation made in Turbo BASIC of these kind of networks, but we are going to go through examples to see how this thing works, what one can obtain from them. And at the end of this video, we are going to go through a little bit of compilation and how to use the compilation of your code to actually obtain a speed up of the program that you are trying to run. Of course, all of these will always be introduced through the use of examples, so that everything becomes very, very clear and very, very concrete. As always, if you haven't done it yet, I would suggest you to go on this link, on these two links actually. The first one practically shows you the Altera emulator for the Atari, so you can get the emulator of the Atari from that website, and you can get it for free. And the second link contains guidelines on how to find Turbo BASIC and even the Atari DOS. So in case you haven't done that, you can use these two links to create the environment that I'm going to use to show all these examples. I will of course report these two links in the description below. Also, if you are really interested in Hopfield neural networks and you want to understand how they work, there is a very good paper from 1982 that is coming from Hopfield, and the title is Neural Networks and Physical Systems with Emergent Collective Computational Abilities. I am suggesting this paper because this is a very simple paper that actually describe all tenets of this kind of networks, and it's a very simple paper to follow. It's also very easy to find the PDF of this paper legally, so I suggest you to go through this paper in case you are really interested in understanding every single detail of the Hopfield neural networks. And as always, I want to thank all of you for continuing to subscribe, to leave comments, and to share those videos with others. In particular, in this video, one of you has made a comment and has made a request, and the request was to actually see how to compile a basic code so to obtain a speed up. So thank you to this viewer for making this request, and that's actually why I will discuss about compilation at the end of this video. Thank you so much for continuing to subscribe to this channel. Let's introduce now the concept of Hopfield networks. What you see on the screen is a Hopfield network, and it's exactly the same one, the one that you see in the left and the one that you see in the right, but I'm going to discuss the one in the left because it's much easier to follow. So Hopfield networks are very different from feed-forward neural networks. These are networks which are made of artificial neurons, and those artificial neurons are essentially connected to any neuron that you have in the network. So every neuron is connected to every neuron. This is what you see with these red lines in the graph that you have in the left hand side. So in this particular case here, we call them N1, N2, N3, and so on until N8. So it means that we have 8 artificial neurons in this particular Hopfield networks. And as you can see, they are all connected with each other. These artificial neurons can, of course, have a value. And what we are going to do here is that we will focus on values that can be either 0 or 1. So every time you see those neurons here, they can only contain a 0 or a 1. And for every neuron, we are going to call this value V. So for neuron, let's say N1, we will have value V1. For neuron N2, we will have value V2, and so on until neuron N8, which will contain the value V8. And all these V1, V2, and so on, V8, they can be only zeros and 1. So what is this plot that we see on the right hand side here? This is exactly the same Hopfield network that you see on the left hand side. It's just that everything has been reorganized in a way. So all the neurons that you see in the left hand side, they are practically in a circle, as you can see. And they just have been reorganized so that they all lie on a line. But as you can see, connections are still there. And if you check, every neuron that you have in this network will be connected to every other neuron that is in this network. So the two networks that you see here are both Hopfield networks, but they are essentially the very same one. There is a reason why I have created the right hand side plot. It's because this kind of neural network can be utilized in many different ways. And one particular way that is very simple to understand and very simple to follow is to use them as content addressable memories. So in practice, it means that these networks can behave as memories, just that these are not, let's say, memories that you can refer through an address, but you refer to these memories through a content. So in practice, it means that if you have stored a pattern in this kind of memory, in this kind of network, essentially you will be able to recover the pattern by simply providing a pattern that is close enough to the one that you are looking for. So if, for example, you store the pattern that consists of N1, N2, N3, N4 being all 1, and N5, N6, N7, N8 being 0, in practice, if you provide a pattern that is very close to that, you are going to get that pattern. So in practice, you could have a pattern that consists of 1, 1, 0, 1, and then all 0 for the neurons from N5 and N8. And by evolving the state of the network, you will be able eventually to recover the content that is the closest one to the initial pattern that you provided. To make things clearer, I have created this other plot here that you can see on the screen, and essentially this is your Hopfield network that has been reorganized in a line, and what you see in practice at the first line here is the pattern that is stored in the network. So this network in this particular case consists of 7 neurons, and the pattern that has been stored consists of 1, 1, 1, and then 0, 0, 0, 0. So the network is going to work like this. Let's suppose that you want to recover this pattern, but you don't remember exactly how this pattern looks like. So you provide a pattern that is the one that you see on the second line here on this plot, the one that corresponds to the line start. So you provide a pattern that is close enough, but it's not exactly what you are looking for. And in this particular case, it consists of the pattern 1, 1, 0, 0, 0, 1, 0. So if you let evolve the neural network, and that happens by iterations, essentially at iteration 1 that you see here on the third line in this plot, the network, or let's say the values that are stored in the network, are going to start to evolve. So in this particular case, what happens is that we lost the one that was in the right hand side of this pattern, and we still have the two ones that are on the left. Then at iteration 2, something else is going to happen until you get to the point that the system evolves so that you recover the initial pattern, which consists in 1, 1, 1, 0, 0, 0, 0. And that also corresponds to the final line that you see here in the plot, which is labeled by AND. So in practice, this is the way Hopfield networks work when you are using them as a content addressable memory. We are going to implement something like this in BASIC so that we can understand in more details how this can be utilized in practice. Before we can develop the code in BASIC, we still need to understand the formulas that we want to implement in BASIC. And the formulas that I am showing here, Formula 1 and Formula 2, are essentially formulas that I have extracted from the paper that I suggested at the beginning of this video. So Formula 1 is essentially telling you that it's telling you how to evolve the neural network. So in practice, if you have zeros and ones that are stored in the neurons, you can evolve these values essentially by using Formula 1. Formula 1 is not extremely difficult to understand. Essentially, you are going to compute a sum, and this sum is essentially the sum over the index j that is different than I, and then you have the sum for the terms tij times vj. And what you check is that if this sum is bigger than some threshold value, which we called ui, essentially the value of the neuron is going to be 1, and if it is smaller than this threshold value, then essentially the value of the neuron is going to be 0. In our particular case, when we implement the code in BASIC, we are going to use ui equals 0 for every neuron. So in practice, the sum that you see here in Formula 1 will be checked if it is bigger or smaller than 0. Then, of course, we want to spend a few words on the coefficients tij. Essentially, you have to think of these coefficients as being pre-computed, and these coefficients essentially tells you what is the strength of connection between the neuron I and the neuron J. The way these coefficients are computed is not extremely complicated. In Formula 2 here you see that we have a Vs with index I and index J. Essentially Vs is the pattern that you want to store in the network, so S can go from 1 to whatever number which correspond to the number of patterns you want to store in the network. And then you have the index I and J that just run from 1 to n, where n is the number of neurons that you have in your network. You have to always bear in mind that TII is equal to 0 because every neuron is not connected to itself. So now we are ready to implement these two formulas in BASIC. So this is exactly what we are going to do now. I have prepared a basic code that implements an Hopfield network, and the very first thing that I am going to do is to list it so that you can see the whole code in its totality. And now we are going to go through every single part of the code, and I'm going to explain what they mean. So the very first part that we would like to see is line 10 through line 45. And of course line 10 is just a remark, but then line 15 start to define a variable. The variable is ether, equal 10. So this would be the total number of iterations during the evolution of the Hopfield network. We are going to consider only 10 iterations and then we will stop. Then at line 25, as you can see, n is equal 9, and n in this particular case is the total number of neurons that you will use in the Hopfield network. Then at line 35 you have another variable called ns equal 2, which is essentially the number of patterns that we want to store in the network. Then since we have defined n and ns, we can also start to do a few memory allocations which are done at line 45, where we define the arrays v and the array t. The first one is unidimensional, the second one is bidimensional. So we can now go further, proceed further, and analyze a different part of the code that goes from line 50 to line 59. And what we do here is that we define the initial conditions of the system. So we have this Hopfield network that has 9 neurons. They can contain a value that is 0 or 1. So what we do here is that we assign a value that is random. So as you can see, we have a for loop that starts at line 52 and ends at line 58. And what we do in this for loop is that we are going to assign a value for every neuron that you have in the network. So at line 54, what we do is we first of all assign vi equals 0, and then at line 56 we shoot a round number and we check if that number is bigger than 0.5. If this is the case, then the neuron has a different value, which is not 0 anymore, but it's 1. And then at line 59, this is just a simple line to print everything on the screen so that we can actually visualize the random initial conditions that have been created by the program. So now we can proceed further and go through line 60 until line 112. And if we list it, as you can see here, we start to define and to store patterns in the Hopfield network. So the very first thing that we do here at line 65, we define a for loop where essentially we are resetting the value of the array t. And all these values are set to 0. Then starting from line 90, we start to store the first pattern in the network. The way we do this is by applying formula 2 that I have shown previously. So in line 92 we have a for loop that starts and that ends at line 112, and this goes through every neuron that we have in the network. So what we do here is essentially we use formula 2, and in practice at line 100 that's exactly formula 2 that is being applied. So if you go through the details of this part of the program here, you will see that this corresponds exactly to the way one should store a first pattern in the network. But we are interested also in storing a second pattern in the network. So I'm going to list another part of the code that goes from line 115 till line 155. And as you can see here, what we do is we still use formula 2, but now what we are doing is we are storing a second pattern. So line 120 starts a new for loop that ranges over every neuron of the network, and this for loop ends at line 155. What we do here is practically formula 2, and if you focus on line 140 in particular, you will see that that's exactly what we are doing here. We are storing essentially a second pattern. The two patterns are different. You can see it from line essentially 93 and line 122. In the first case, we are practically storing a pattern that has only that has zeros in the left hand side of the network, and everything is 1 in the right hand side of the network. And in the second pattern we do exactly the opposite. So the first part is made of ones, and the second part is made of 0. So we are now ready to go through the rest of the code, which goes from line 160 to line 190. And this is the evolution part. So in practice here, what we implement is Formula 1 that I have shown previously. And you have a for loop, and that runs that starts at line 162 and ends at line 190. This is essentially a for loop over the number of iterations. Then you have a second loop that starts from line 165 and ends at line 183. Essentially, this is a loop that is running over every neuron of the network, and you have another nested loop that starts from line 172 and ends at line 177, and this is exactly where we compute the sum, so that then we can compare the sum with 0 and understand if it is bigger or smaller than 0. This is exactly what we do at line 182. Eventually, once all these iterations have been done, at the end of every iteration we are going to print what we have. This is done at lines 184 and 185 and finally 187. So these 3 lines here are just to show the code. This part of the code is essentially the evolution of the Hopfield neural network. We are now ready to run the code, so I'm going to type run and hit enter, and as you can see at line 0 here we have the random pattern, and then very quickly, already at iteration 1, it finds the pattern that was stored in the neural network. In this particular case, this is the one that consists of 1 1 1 1 and then 0 0 0 0 0. But as you can see, we started from something that was let's say quite chaotic, but close to a pattern that was stored in the network, and it did found what was the corresponding pattern through running in practice the evolution of the system. We can run a different example here. You will see that this is going to provide different results. It's also interesting to see how these work in terms of execution times. As you can see, it does take some time to find the final pattern that was stored. This is another very interesting example that you see here, because we started from a pattern this time that was different. It's still a random one, but one pattern that essentially has a lot of ones on the right hand side of the patterns rather than on the left hand side. And so the pattern that was found already at iteration 1 is a different pattern compared to the previous one that we just run. Let's try now to compile this program and see if it runs faster. So the very first thing that we need to do is to go back to DOS, which I'm doing right now, and we are going to compile this code. So the first thing that I'm going to do here in DOS is to list every file that we have, and as you can see here we have a compiler. This is the 4th row in this list. So we are going to load the compiler, which is made like this. So you first type L and then you provide the name of the compiler and hit enter. And now we are in this new environment where we have to specify what drive number we are using. In our particular case it's 1, so I'm going to push 1. And now you see that the list of files that we have on the first device appeared, we want to compile in particular this program here, which is called Hopfield.bas. This is exactly the one that we would like to compile so that we obtain a faster execution time. So I'm going to push enter here, and as you see, it has spent some time in the compilation. Now it is asking me, the system is asking me how I would like to save this compiled file. I'm just going to provide the same name, Hopfield, and extension will be different. It was .bas before, now it's going to be .ctb. So I'm going to put to enter, and I don't want another copy, so I'm just going to say no. And now I'm going to type Control D because we want to go back to those. We want to run what we just compiled. So now if I list the files that we have in the first device, you will see that there is now also a runtime in the list. And this is the 5th row in the list that you see here. So we are going to call the runtime, we are going to load it, and the way we do this is by typing L again, and we call the runtime.exe this time. So if we do this, you see here that the runtime environment is asking me what to load. So I'm going to hit L, and I'm going to enter the name of the file, that was this one here. And if I now hit enter again, this is going to run the compiled version of the code. And as you see here, this is way faster than what we would obtain with the code that was not compiled. If we run this code in the Turbo Basic, clearly this runs slower than what we just have seen here. So this completes this video for today. As always, I want to thank you for being here. I want to thank you for your attention, and I hope to see you next time.